Right, so this is Ben, I'm Mikhail, and we work for Carolon Global Solutions, Ireland. And this topic of this talk is building an expression parser in Python. Here's the plan. First of all, we'll look at why we even needed to do this in the first place. Then how to implement expression parsing and execution. Then which options we looked at for doing that. Then we'll take a closer look at the library called Lark and go through all the specifics of Lark Python library, and then we'll see how we integrated it with other tools and what optimizations we did and what we didn't do but can do in the future, right? And also where this library can be applied besides that exact tasks. So let's look at the task we had at hand. What we wanted to do is to create a rules engine for our enterprise context, right? So the exact task we had a list of JSON objects. Each object should come through a list of rules, and the rule will check the certain conditions, certain business logic based on the fields from this JSON object, and then return true or false. And every rule also has a predefined answer, like whatever it is. It could be an action, or it could be a kind of an object to sort them out, or something like that, or priority in some point. So it gets a bit clear after all, right? So every rule should be an expression in some sort, because we wanted business people to go and tweak these rules. So every rule should be able to be changed by a person who is not an engineer, right? So sort of a low-code platform. And as our inputs are always JSON objects, they could be nested, and they could include things like lists or weird stuff. So we wanted to integrate JSON path expressions inside our expression language as well. So, for example, simple example, right? We have a list of objects with a predefined set of fields. It's a kind of what kind of an object it is. Here, for example, it's an animal. There is a name of the object. In this particular business process, it's irrelevant. Let's say it also signifies what it says and if it has any fur, right? So then we can design a simple set of rules. For example, the first rule will look into the object, and if you can see the $sign means it's a JSON path expressions, JSON path query. So it takes the field called kind and checks if it's equal to the string animal, right? Then we decide it's an animal. There is a second condition to check if it has a fur, and if it says meow, then we can believe for some reason that it's a cat. The second rule is checks the same, but it shouldn't have any fur, and it shouldn't say anything, right? Then we can say, well, it's a snake. So if the first rule returns true, it's cat, right? If it doesn't return false, if it returns false, then we check the second rule, and if it returns true, it's a snake. So something like that. But you can use that in a lot of different cases, right? What's important is that every rule is a Boolean expression of sorts. It could have and, or, it has equality, it has all kinds of operators, right? But in the end, it's just a Boolean expression that returns true or false. So you can implement it in various ways, right? But what we decided is that it will be an expression, sort of formula in the language we design ourselves. Right? So here's the options we looked at for making this. So first of all, we could go and implement the language ourselves, right, from scratch. Second of all, we could go into and integrate some kind of Rust library, which is fashionable these days and gives you a lot of performance. And we needed performance. What I forgot to mention that we needed to process hundreds of thousands records in a day. So every object should be processed in milliseconds. Right? So a library written in Rust would help with that. Another option we looked at was AST library, Advanced Syntax Tree, I think it's called, which is built in the standard Python library. And the last option we looked at was a Python library, fully Python, called Lark. And spoiler alert, that's the option we chose. So option one, write from scratch. So implementing an expression language is basically two-sided. First of all, you have a string of an expression, you have to parse it and create a syntax tree in memory. And the second part is actually executing that structure, which will give you an answer. You will transfer the tree from the ends of the branches. They will, and you visit every node and execute every node. Every node returns something. That node will become a parameter for the next node, and so on, until it all converges to the root of the tree, which gives you the answer of your expressions, right? So for parsing, it's not really a rocket science, right? For parsing, computer scientists, very smart people, already designed a number of algorithms to parse a string in a programming language or any language, right? Some algorithms are more for non-deterministic languages, something closer to a natural language processing, right? That's not what we needed. We wanted to define our syntax, our grammar. So we needed an algorithm that would just go and parse a predefined grammar, right? Then you need, when you have your syntax tree, you need something to traverse the tree and execute it. That we would just need to write ourselves. It's not a huge task, but still it's a task, right? And it requires some effort, and there could be potential bugs in it. And if you have bugs in your programming language, it's not fun. I've been there, I don't recommend. And we had to maintain a strong performance, which will require performance testing and so on and so on. So second option is to take one of the Rust-written libraries and integrate them. And there is a number of them for your disposal, but it would require an overhead of integrating this into Python, creating a package, creating a deployment pipeline that would package it and integrate with the Python project and so on and so on. The option number 3 was to use the built-in library called AST, and it basically requires to parse Python and execute Python. And it works fairly quickly, and it's all right. But the downside is that Python is a common-purpose language, so your expression would be able to open files and make HTTP requests and so on. It's a security nightmare. So the way we could do that, and we could create a whitelist of allowed operations and allowed functions. So it wouldn't be included in parsing part, But when we actually traverse the tree and execute the result of parsing, we would need to check every operation against the whitelist, and if it's not allowed, we'll just crash, right? So that could be fun, but the downside is that you can, it's hard to control the performance in this case, and if you forget something, something slips in your whitelist, it's a security risk all the time. And also it dictates your syntax, because it can be Python and can be anything else, right? So it's kind of an overkill for this particular case. So Lark. Lark is a fully Python implemented library. It has thousands of stars on GitHub. It's very well maintained, and it allows you to create a grammar using a sort of a DSL for describing grammars. So you don't have to write any code actually to create a language. You just write a grammar in a certain way, and it will create a parser for you. And it also has a framework to write the execution part, to traverse the tree, and it's very easy to use. It's perfect. And it's fairly quick, as much as Python can be quick, and it's very flexible. So here's the example of a grammar, right? It's using a language called EBNF, which is an international standard for describing grammars of programming languages. So it can be, in theory, transferred to a different library, right? So it looks weird, but once you get it, it's very easy to design a language and then add more operations or change the existing ones and so on. Also, Lark gives you some predefined shortcuts, right? You can see at the bottom, it's import signed number or CNAME or things like that, escape string. Things, it's just library of macroses, basically, to include in your grammar, right? Then you get a syntax tree when you parse it. And here's the class that just follows the framework that Lark provides. You just define, for every operation, you just define which code will be executed, what it will return. And you can see how we integrated JSON path in there. So we just decided that every variable that starts with $, is actually a JSON path request. So whenever it comes to the JSON path, it will execute the JSON path query and look into the input object. What else Lark can do? So you can visit its GitHub page, right? It can do a lot of things. It it allows you to implement a standalone parser for certain grammars. So it has an online IDE where you can design languages and execute them at the same time. It has implementations for JavaScript, if that's your thing, and for Julia. There's a lot of existing projects that use Lark already under the hood. For example, Poetry, as a popular package manager, uses it to parse TOML files. Okay. And you can integrate Lark with other tools, as we did with JSON paths, and you can add more context to your expressions. It's very easy. What we needed is a good performance, right? So Python, what we realized is that the parsing part is actually very slow if you do it in Python. It requires creating a lot of objects in memory, which Python is not great at. So parsing will always be slow. If it's implemented in Python, there is no way around it, right? But what you can do is you can pre-parse all your expressions when you start the applications, and then you have them in memory in the form of syntax trees. Then it's very quick to execute them. It doesn't matter if it's Python or not. It's quick enough. And what we also realized that our JSON pass queries also can be pre-parsed. It uses the same technology under the hood, basically. So we managed to do it in milliseconds to process every object, right? We can also improve that. We can add more stuff to the language. For example, we're thinking now to add brackets. Brackets mean whatever it is in brackets is the expression itself, right? So you can create nested kind of executions. You can do a lot of other things. You can do parallelizations, for example. So different branches of the tree, when you execute them, they can be executed in parallel, and then you can synchronize getting the results. It can become fairly complex, but it's possible in theory, right? Lark has a lot of examples on their website. It can parse JSON. It has a parser for CSV in the examples. Or it can do calculations. Or you can go and design a full-fledged Turing-complete programming language using Lark alone. You can, in theory, do some natural language processing, but it's probably not the right tool, right? So the conclusions are that Lark is the best, it's great, but you have to consider the performance implications because it's Python. And if you do something like natural language processing, it might be too slow. Or if you design a common purpose programming language, it also might be too slow for you. But if you want something like what we did, simple expression executor, it's a great tool and maybe even perfect, right? Thank you.
Did anyone suggest RPN?
What is RPN?
The HP-like syntax for HP calculators.
Do you think business people would understand it?
Oh, I hoped. Sorry, it was a joke. I suggested RPN.
Yeah,
it was the very beginning.
We planted this guy in the room to ask questions.
Very often, if you generate a parser and then you feed it with some input, and this input is ill-formed, often the error messages are not really user-friendly if it's not a handwritten parser. Did you experience the same problem with Lark?
No, if your issue with the expression itself, it's a parsing error, it gives you a pretty good parsing error. Yeah. And if the problem with the input and it's a runtime error, you design it. Thanks a lot, guys.
Thank you. Thank you.